Thanks. Thanks for inviting me to this conference. I was ice skating yesterday, and it's quite a change. I hope my body doesn't give me problems from such big temperature changes. I'll talk about 100 gigabit for content distribution networks. If I'm looking at the program, I don't think that's this is an optical hardware crowd here, so I'll try to give you the overviews, but not to go too much into technical details. What are the market drivers for 100 gigabit? I'm probably preaching to the choir here. We see video growing very fast, and video, of course, is a huge bandwidth driver. People are willing to pay for it, especially high-definition content, like video on demand. We did a couple of modeling scenarios, and we believe that within a few years in the metro access portion of the network, 90% will be video. And that's the case even if you store popular content very close to the consumer. That comes from the long tail in the video distribution. So that's actually good. We love, my company loves to sell bandwidth, and I guess your company probably loves to sell bandwidth as well. So that's good for all of us. Now, video has some pretty important requirements. You have to have low latency for good picture quality. You have to have a very resilient network. But then also there are a couple of things that can be easier with video. For instance, you can optimize your network in an asymmetric way to take advantage of the, that you require much more downstream bandwidth. Other important bandwidth drivers could be storage networking, carrier wholesaling, science applications, grid computing. And I hope they all will take off as well. There has been a big religious battle between what should be the next Ethernet standards. Today it's 10 gigabit Ethernet, and there was a pragmatic camp that was advocating 40 gigabit Ethernet, and then there were the more visionary people who were advocating 100 gigabit Ethernet. Ethernet has been growing in steps of 10, in factors of 10, starting with 10 megabit Ethernet. Clearly, 40 gigabit Ethernet is technically easier because 40 gigabit exists today. 100 gigabit is harder, but 100 gigabit is sort of more beautiful. So the two camps in the end came together, and there will be both the 40 gigabit Ethernet standard and the 100 gigabit Ethernet standard, and that's for my company that's perfectly fine. We believe that 100 gigabit will be cost effective compared to 10 gigabit, not only on the CAPEX but also operation cost. And it will actually help both 40 gigabit and 100 gigabit. 40 gigabit today is pretty expensive compared to 10 gigabit, but prices are coming down. So what are the benefits for 100 gigabit networking? If you look at today's routers, they are reaching terabit and multiple terabit of capacity. And the capacity is actually not limited by the switching capacity of the router, but more of how much I/O capacity can put onto the router. And clearly 100 gigabit will help there to get the full switching capacity. You could, of course, have logical 100 gigabit ports, but still use 10 gigabit transport, and that's being done today. But this is expensive. Eventually, the higher speed interfaces always are cheaper on a per bit basis. It's also better to have higher speed ports just for the stat muxing gains. If you stat mux up to 100 gigabit, you get much better efficiencies than if you have to stat mux only up to 10 gig. And finally, in your WNM network, each channel burns up a wavelength. So clearly, if you go at 100 gigabit, you're going to burn up 10 times less wavelength. So there are many benefits to 100 gigabit networking, just as there were benefits to 10 gigabit networking 5 years ago. When you look at increasing capacity between point A and point B, there are several options you have. Option number one is to increase spectral efficiency. So you have a certain amount of bandwidth, and that's defined by your amplifier, and you just try to cram more bits through this bandwidth. What you could also do is increase that bandwidth, use multiple amplifier bands, or also just light another fiber. Now, the latter two options usually are expensive, not always, but usually they're expensive, especially having multiple parallel amplifiers. So people really try to do is just to have higher spectral efficiency. And that's very similar to what happened in the wireless space too, where people just try to get more and more bits into a limited amount of bandwidth. If you look at other requirements for WDM systems, often you install a WDM system, you don't know exactly what's the traffic growth is going to be. So you lay it out maybe for 10 gigabit, but then you want to later on upgrade this 10 gigabit to 40 and 100 gigabit. So your 100 gigabit channel should be compatible with a system that has been designed for 10 or 40 gigabits. And that usually means it has to be it has to fit on a 50 gigahertz grid. That's the channel spacing of the WDM channels. It also has to go through ROADMs. ROADMs are devices or like optical switches where you can direct wavelength channels without converting them into electronics. So ROADMs are very low-cost switching devices that have huge capacities. But of course, if the ROADMs have been designed for 10 gigabit channels and now you come with 100 gigabit channels, it still has to work. Also, when you lay out a system for 10 gig, it goes over a certain distance. You want to make sure that when you upgrade it to 100 gigabit, you still reach the same system distance. So what I'll show you that 100 gigabit with an advanced modulation format actually allows you to achieve all these things. So it's really to have high spectral efficiency and be compatible with existing systems. So this is a mini tutorial on modulation formats. If you look at 10 gigabit systems today, even 40 gigabit systems, they have a very simple modulation format. It's just a light on and off. It's like a flashlight with a shutter. And that's very simple. You only need a shutter. It's very simple optical hardware. However, it requires a lot of bandwidth. And typically, a 10 gigabit system requires 10 gigahertz of bandwidth. A 40 gigabit system requires 40 gigahertz of bandwidth. And a 100 gigabit system would require 100 gigahertz of bandwidth. 100 gigahertz is pushing it electronically. So as you go higher and higher in speed, this becomes much, much more difficult. What's also true is that if you have a high bandwidth, all your impairments of the signal, as the signal travels down the fiber, it gets distorted. The more bandwidth you have in the signal, the more distortions you get. So what is more advantageous at 100 gigabit is to use a more complex modulation format where you get multiple bits per symbol. And you do that by basically modulating the amplitude of the signal, by modulating the phase of the signal, and by modulating the polarization. And that's how you get 4 bits per symbol. The price you pay is much more complex receivers and transmitters, much more complex transmission hardware. Now, if you go to higher, more complex modulation format, what usually improves is the transmission performance. So all the distortions or have less of an effect. I won't walk you through the numbers here, but again, if you pick a more complex modulation format, a more sophisticated modulation format, 100 gigabit has roughly the performance in terms of transmission of 10 gigabit systems today, and that's very good. Not exactly, but it's roughly equivalent. So for 100 gigabit, clearly there has to be a sophisticated modulation format, otherwise you couldn't go over long distances. And you couldn't go over systems that have been designed for 10 gigabit. So the best modulation format is Polarization Division Multiplexing Quarter Phase Shift Keying, PDM-QPSK. So you don't need to remember this acronym, but it's really you modulate amplitude, phase, and polarization. And this is a coherent system. So this works pretty much like your FM radio in the car. You have a local oscillator, you beat the local oscillator with the incoming signal, and that's how you get your original data back. This has a couple of advantages. All linear distortions can now be basically undone digitally, and that is a very, very good advantage. It also allows you to be transported over systems that have been designed for 10 gigabit, and you can have neighboring channels that don't bother you. So all those advantages make this format very, very attractive for future 100G systems. We have done tests of 100 gigabit systems. We sent 16 terabits over 2,500 kilometers of fibers. Those were 164 channels spaced by 50 gigahertz. So the fiber here carries 16 terabits of information. So, and clearly you can go several thousand kilometers using this modulation format. And that's what network providers pretty much require, 1,000 to 2,000 kilometer reach and 50 gigahertz channel spacing. So what we see as a vision is you have a transparent optical network, a cloud, that you start out where you have transmission fibers and optical switches like ROADMs, optical add-drop devices, where you may start out with 10 gigabit channels, and then as your traffic grows, you do edge upgrades from 10 to 40 to 100 gigabit, but you don't change anything at your optical cloud. So this allows you very, very cost-effective upgrades and upgrades without a forklift in the optical domain. Of course, this requires to have colored optics on your service equipment, like your IP routers or your Sonic boxes, and it also requires some commonality in the management plane. This just shows you that at 100G, the filtering impact can be fairly benign if you use the right amount of the right modulation format. What we did is we did a field trial with Verizon a year ago, where we took a live system that was carrying 10G channels between Tampa and Miami, and we put in a 100G channel and transported video over that live system that was installed, and we got an excellent quality reception. So this shows that you can take existing systems that carry live traffic, upgrade the channel from 10G to 100G, and you don't bother anything else that's on the system. And obviously this is very, very important for our customers, because they would hate to install systems today that they have to rip out tomorrow to make room for 100G. So backward compatibility for 100G is a critical feature. This just shows you, this is very technical here, some of the bit error rates, but it shows you also shows you on the right side here that you do have real channels, real live channels next to the 100G channel, and there is no impact, no negative impact. Coming back to the receiver and transmitter technology, as I said, a more complex modulation format requires more optical hardware. And with that new technology, this can become expensive. However, at Bell Labs, what we are developing very aggressively is photonic integrated circuits that allow you to collapse all this complexity on a single chip. And this is the equivalent to the integrated circuits in electronics, where you have very complex functionality on a single chip. So we believe that these photonic integrated circuits will allow the basic cost of 100G to be very compatible with today's 10G systems. And they have also comparable footprint and power consumption. Those are other very, very important aspects. Footprint and power consumptions are critically important to be low for 100G, otherwise you can't fit it in existing line cord slots. This is just another example of a very highly integrated transmitter that actually uses even more complicated modulation format, 16 QAM. That's a modulation format that's used in wireless systems today. On my last few slides, I want to look a little bit into the future. If you look at 100G, if you really have 100G demand between two endpoints, of course, then you will put in a full 100G wavelength. But it could be that on day one, you don't really need 100G, you need something less. In which case, you could put in a 10G first and a 100G later. But what actually the 100G, what you could also at 100G is optical packet switching. And that means you basically quickly change the wavelength color of a channel. You switch between a 100G channel between red, green, and blue, and then just by optical filtering, you can now direct the red, green, and blue data to different endpoints, and that's what's called optical packet switching. And that allows you to share, for instance, a 100G channel between multiple endpoints in an all-optical way without having to go through optoelectronics and do their routing. So this is called optical packet switching, it's called optical burst switching, it's called optical grooming if you go into literature. This, at 10G, I think the value proposition for that is marginal, because at 10G probably most channels are filled and you don't need to have a sub-wavelength grooming. But at 100G, I think this is very attractive. And we believe this could be, future 100G systems could offer optical packet switching options. This is just a demo we did a few years ago at 10G doing exactly that. One key technology you need here is a laser, a transmitter that can very quickly switch colors within a few nanoseconds. So you could really send packets, you could really color your individual packets. But those lasers are available today, and you can indeed switch them very quickly. So takeaway messages from my talk. Video will dominate network traffic. That's probably not anything that is news to you. We believe that 100G will be very cost effective and will satisfy network demands, but it will require a sort of a new modulation format that's not been used today at 10G or 40G. What's really critically important is that 100G is backward compatible. And if you use an advanced modulation format, it will be backward compatible. To make the 100G cost competitive, you really need a new technology, and that's been done with Photonic Integrated Circuits. They are very low cost, low footprint, high reliability. They can be mass manufactured. We also believe that new technologies like optical packet switching may become attractive at 100G. Because they allow you sub-channel wavelength connectivity. And so to summarize, we are very excited about 100G, and I think it will enable massive content networking. It will make content networking really cost effective. Thanks a lot for your attention.
Any questions? Answers?